So can I start now, Nutan?
Yes, sure.
Welcome everyone. So today we have Dr. Nutan Limaye. Before I introduce her and we proceed with the talk, let me just mention two things. The first is that please use the chat box to send any questions that you might have during the talk, and I'll put it to the speaker at the end, or if the question is very important, then during the talk as well. And the second thing is, if there is any issue with the connectivity via Zoom, then you can also watch the talk online on Facebook. I'll share the Facebook Live link in some time, and you can just copy it and keep it. Let me introduce our speaker today. We have Dr. Nutan Limaye. She's an associate professor in the Department of Computer Science and Engineering at IIT Bombay. She did her PhD at the Institute of Mathematical Sciences in Chennai. And then she went to TIFR Mumbai for a brief period of time, and then she joined IIT Bombay. She's associated with the Association of Computing Machinery, ACM, which is the highest body in computer science, as the vice chair of the ACMW since 2019. And her research interests are in theoretical aspects of computer science. And today she's going to speak about complexity theory. And the title of her talk is How to Prove Something is Impossible. The charm in proving something is impossible, a complexity theoretic field. So Nutan, thank you so much, and please, you can start.
Okay. Thanks a lot for inviting me to give a talk in this webinar series. It's a fantastic effort, as I said, and I'm very happy to be a part of this. Also, thanks for the introduction. Okay, so let me get started with today's talk. We are going to talk about proving impossibility results, and we are going to take a complexity theoretic perspective towards this. So, you all may have seen a proof in mathematics where you show something is impossible. Suppose I ask you, can you write square root 2 as a fraction of two integers, say? Then you will think about it a little bit and say that no, it's not possible. I'll say, just prove this to me. And there are several elegant proofs of this fact. Let's look at one standard one, say. So suppose square root 2 was a fraction of two integers, then we can write it as p by q, where they don't share any common divisors, common factors. You square both the sides, and you will see that p square is 2q square, which means p square is even, which then means p is even. But that means p square is divisible by 4. Running a similar argument for, say, q square, we can also see that q square is divisible by 2. And therefore, q is divisible by 2. And overall, as a result, we can say that p and q have a common factor, which obviously is a contradiction to our initial assumption that p and q do not share a common factor. Okay, so here was a statement in mathematics that which asked you to write square root 2 as a fraction of two integers, and then you proved to me that in fact it is not possible. All right. So this is a typical mathematical proof for showing something is not possible. And what do I mean by a complexity theory perspective of this? So usually when we move from mathematics to slightly computational questions, one important aspect that changes is that in computation, you are given certain resource bounds for performing certain tasks. And often to optimize those resources is the name of the game. So for example, when you're given a computational problem, you will ask things like, can this be solved in time so and so? Or can this be solved in space so and so? So these are the typical computational questions. And here what we are going to talk about is showing impossibilities of such statements. Okay. So imagine I give you a concrete example. You are given a graph. I hope everybody knows what a graph is. It's a set of vertices connected by certain edges. And now I ask you, can it be properly colored using 3 colors? So by proper coloring, What I mean is, if two vertices are connected to each other, then they must get different colors. Okay. So look at this coloring of this graph. If you pick any edge in this graph, you will see that the two endpoints have different colors. Okay, and I have used overall only 3 colors in this. So this in fact shows that this specific graph is properly colored, can be properly colored using 3 colors. Now, if the number of vertices in this graph is say n is a parameter, it is a parameter that comes along with the problem statement because your graph is given to you. So you know the number of vertices in this graph and say that number is n. Now I may ask you, can this problem be solved in time n cube? N cube I've just written as an example, maybe n to the 4, n to the 5 time steps. Okay. And another question is, can this problem provably not be solved in time n cube? The second statement written in red is asking you to show some sort of impossibility. Yeah, because I'm going to tell you that no matter how clever you are, you will not be able to come up with an algorithm for this problem that runs in time n cube and gives a valid answer to the question that is being posed. Okay? It is very easy to see that there is a very inefficient algorithm for this problem. Okay? That runs in time 3 to the power n. Instead of n to the power 3, which is what I'm asking, there is a simple algorithm that runs in time 3 to the power n. Okay, that is a small exercise. You can try to think about it later on. Okay. Now, I did not pick this problem to tell you about very arbitrarily. This problem is a very important problem in computer science. It's so easy to state. But if you answer any one of the two questions, so either you give a positive answer by designing an efficient algorithm that solves this problem in time n cube, or you show somehow by proving impossibility that this problem is not solvable in time n cube. For either one of these answers, you will receive $1 million. Yeah. Most people believe that, in fact, it is not solvable in time n cube. And there is a whole $1 million prize attached with this. Okay, we'll come back to this problem later. These problems are called NP-hard problems, and we will talk a little bit more about it later on. But if you heard about NP-hard problems, these are these million dollar questions. And if you answer one of these two questions correctly, with a proof, of course, then you will receive $1 million. Okay, so here written in red is a typical impossibility question that comes up in computation. You're given a problem and you're asking whether the problem can be solved in the given amount of resources. In this case, the resource is n cube time. I hope this part is sort of clear, the kind of questions we will look at. So first question to address is, why should we try to prove computational impossibility? Okay. Apart from, of course, receiving $1 million, which is very nice, obviously. But what are the other reasons for which you may want to prove computational impossibility? So this actually, computational impossibility lies at the crux of some of the developments in computer science. Firstly, just from a philosophical point of view, just like in mathematics, in computation too, proving roadblocks tells us where not to look for solutions. So if tomorrow some next generation of students start designing algorithms for these problems, if the previous generation has already proved that n cube time algorithms are not possible, maybe they can spend their energies better designing other types of algorithms. And this is true about any impossibility result, in fact, that if it tells you where not to look for solutions. So though proving impossibility results may seem like a very pessimistic task, oh, you can't do this, you can't do that. Today, when so much positive messaging goes around that you can do everything you put your mind to, well, there are actually certain resource bounds or certain constraints that we all work under. and certain things are actually not possible to do within those constraints. And it's good to know that. So just from a philosophical point of view, proving such results is very gratifying. In computation, it also helps us understand the power of computational resources. So it tells us, if n cube amount of time cannot solve a certain question, it tells you something about the n cube amount of time as well, that it is constrained in a certain way. Another very important reason to prove impossibility results is cryptography. You may have heard that there are these very hard to compute functions like factorization and so on, based on which our entire cryptography works. So it also has some real life applications in some sense, right? So assuming that we are able to prove that there exist these really hard to compute functions, under this assumption, we are able to do public key cryptography, for instance, and so on. Okay? So here, that is another very concrete reason why one would want to prove impossibility results. And one another slightly aesthetic reason, or maybe very selfish reason for mathematicians is it leads to beautiful mathematics. So time and again, when people have managed to prove such results, they have discovered some really beautiful mathematics as well along the way. So this was a kind of a pitch from my side to why one would want to prove impossibility results. And hopefully many of you are with me so far. So let's see now, how do we prove impossibility results? Okay. And in order to show how to prove impossibility results, let me just run you through a couple of simple puzzles. Okay. So let me start with my first puzzle. Okay, so puzzle number 1. You have a very expensive wristwatch and your annoying younger brother has decided to play a game with you. He's hidden it from you and he's decided to play a game with you. He's put these lots of these glasses and he says that, look, your wristwatch is under one of them. Okay. You can ask 2 types of questions to your brother. Is the watch placed after glass number I? You can ask that about any I. Or is it placed before the glass number I? He's going to be truthful. So he will either say yes for your question or possibly say no. And to answer each question, he's going to charge you 1 chocolate. Okay. So his answer is going to be either yes or no. I hope the puzzle is clear to everyone. Okay. So now let me ask you this question. How many chocolates can you get away with to recover your watch? Okay. You want to, of course, as a giver of the chocolates, you want to spend as few chocolates as possible. As the receiver, he wants as many chocolates as possible. All right. So here is a very simple strategy that you could use, which is for each position I from 1 to etc. Say there are n glasses, then for each I from 1 to n, you can ask if it is placed before the glass I. Okay, so you ask for 1, you ask for 2, you ask for 3. If you apply this strategy, okay, then there exists a positioning of the watch, which is in fact under the large glass, which will enforce you to pay n chocolates to your brother. So this is called the worst case analysis of the problem. That is, you use this strategy in the worst case, that is, for the worst possible placement of the watch from your point of view, you will end up paying n chocolates to your brother. Now, n seems like a lot of chocolates. I mean, say you had 10 chocolates, but there were 100 glasses. Can you perform this task well? So now the puzzle is the same, but I've put this constraint on top of this, that you have only 10 chocolates, but there are 100 glasses. And some of you may have seen this strategy. It is called the binary search strategy. So you want to search the watch among n glasses. What you could do is, let's say I define my beginning to be first and my ending to be last. And I compute the midway point of this current interval first to last. And I ask midway in the entire current range, is the watch before mid or after mid? Suppose the answer is yes, that it is before mid. Then I know it is not in the second half. So I change my focus to the first half of the interval. So make my last become mid. And if the answer is no, then I have to focus on the second half of the interval. So I make my first go to mid plus 1. And I repeat this process. This is a typical binary search example. And I don't know whether you've seen the analysis of this, but this will end up making you pay around log of n. Log is typically taken to the base 2 in computer science. So log to the base 2 of n. Okay. You may wonder where this log is sort of coming from. So if you have not seen this before, let me kind of do a short analysis for that. So you are searching in the range 1 to n. Okay? So let me write a recursion for how many chocolates you're paying. If I am searching in the range 1 to n, then first I end up paying 1 chocolate to ask a query about the mid. But after I receive the answer for this query, I know that my search can be restricted to a size n by 2 range. So I made progress by paying 1 chocolate. I made progress from n to n by 2. Yeah. So now you're paying 1 chocolate every time and reducing your range by half. How long can this process go on? Right? N by 2 will become n by 4. N by 4 will become n by 8, and so on. And of course, when you solve this recurrence, you can quite easily see that search n will be close to around log n. Okay. So indeed, if there were 100 classes and we are taking log to the base 2, in fact, using far lower than log 10 chocolates, whatever is 100 log 2 number of chocolates, you were able to find your wristwatch. Right? So, great. But I have not talked about computational impossibility so far. I'm just giving you algorithms. So let's bring in the impossibility angle into our discussion. The question is, you are the giver of the chocolates. So you want to optimize somehow. So the question is, can we do better than this? Can you find the watch by giving away fewer than around log n chocolates? Okay. So let's look at a specific instance. Suppose you had 16 glasses. Okay. And your watch was in glass number 9. Now, by giving 1 chocolate, you may realize that the watch is in the second half. You'll give yet another chocolate to realize that it is in the 1/3, the 1/4, the range between 9 and 12. You'll have to spend 1 more chocolate to sort of figure out whether it's in the 9 or 10 range. And then you spend 1 more chocolate to figure out it is in fact in glass number 9. So for this example, with this placement of watch, of your wristwatch, you've spent 4 chocolates. But there is a little bit of a thought to be given to this reasoning. Yeah, because what this example showed was that the specific algorithm, which I call binary search, that algorithm cannot do better than spend log n chocolates. This example is telling us that look, and this example you can generalize. Yeah, for n, I'll just put it just one after the mid, and I will be able to recreate it for any n, this log n bottleneck. But remember that this is only being done for this binary search algorithm. So, but the question, when I ask you an impossibility result, it's asking something more. What we are really asking is there any algorithm that can do better than log n? So we were clever enough to come up with a binary search algorithm, but maybe there is some other intelligent body sitting somewhere who may be able to come up with even better algorithms. That is not ruled out by what we just showed. The 16 class example, which I said we can generalize later, which can be generalized, just shows that that algorithm that we came up with in less than 5 minutes, say, cannot do better than log n. But when I ask you to prove impossibility results, I'm asking for much more. And that's where the whole challenge of proving impossibility result lies. You know, you're not just asking whether a certain algorithm does not do better than its stated performance. It is asking that there is no algorithm that can do better than this, better than the bound given. So the question is algorithm independent in some sense. It's trying to defeat every possible algorithm that any intelligent person can come up with. Right? So here is a task that we are supposed to execute. We have to show that. So I will to break the suspense. In fact, log n is a lower bound. That is to say, no algorithm can do better than log n. Okay, but how does one prove such a thing? We can't sit and enumerate all algorithms naturally. Our lifetime is not enough for that. Right? So we have to be able to argue impossibility without actually looking at every algorithm and saying, look, for this algorithm, this is a bad example. That algorithm, this is a bad. We cannot possibly do that. We have to abstractly argue about impossibility without really knowing the algorithms we are trying to defeat. Here is where the challenge of showing impossibility lies. This, of course, comes up with mathematics as well, which all of you would have definitely seen. Yeah, but just to kind of underline that fact that it is a kind of a meta thinking is required. Okay? So let's look at how to prove impossibility in this case. So I will go ahead and boldly claim no algorithm. Though I don't even know the algorithms I'm talking about, I can guarantee you that there is no algorithm that can do better. Okay. So let's abstract out the algorithms we are talking about here. The kind of questions I'm allowed to ask are whether the thing lies before I1, whether it lies before I2, and so on. So any algorithm which is asking such queries can be thought of as a tree whose nodes are these questions, and depending on what answer you get, you ask the next query. So you can depict it as a nice tree. And each leaf of this tree represents a specific positioning of this watch. Okay. So, for example, when the watch was in glass number 9, what were the kind of questions that got asked? We asked whether it is in glass numbered less than 8. When we received an answer no for it, we asked whether it is it's before 12. When we got an answer yes for it, we asked whether it is before 10. And then when we got a yes answer for that, we asked whether it is before 9. Right? So finally, when we reached the leaf, we were sure that the watch is in that position. In fact, because we've drawn it as a tree, we will not stop asking questions till we are sure. So every leaf will uniquely represent a positioning of the watch inside these classes. All right. Now there are n possible distinct placements of the watch. There are n classes, so it could be under 1, under 2, etc. up to under n. So there are n leaves in this tree because each tree uniquely represents a positioning of the watch. And now you can appeal to a simple graph theoretic fact that any tree that has n leaves has depth at least log n. Right? It's a binary tree. We are using that also. So every tree that has n leaves, it could have depth n also. So suppose it's a very skew tree which just goes yes, no, etc. Like suppose had we asked the question, is it before 1? If it had said yes, our tree would have been terminated. Or we would have asked, is it before 2? Is it before 3? The depth of this tree would have been n. But the one which we designed later on, which was binary search, it was kind of log n, the depth of the tree. Depth of the tree represents the number of questions you need to ask before you get to the correct answer. That is basically the number of chocolates you need to spend. And now, because any tree that has n leaves must have log n depth, we get that no matter which algorithm you deploy, you must spend at least log n chocolates. Okay, so that's your lower bound proof. That's your impossibility proof. Yeah, you note that you did not argue with respect to a specific algorithm at all. You abstracted out all these algorithms into a combinatorial object, in this case, a simple tree. And then using certain properties, combinatorial properties of that object, you were able to argue about the behavior of all possible algorithms that look like that combinatorial object. And this is usually how lower bounds are proved. So I will even make a very bold statement by saying many lower bounds will have this pattern that you abstract out the lower bound, the model with respect to which you want to prove a lower bound as a combinatorial question. And then when you answer that question satisfactorily, it says something about the what shall I say, the restriction or the shortcomings of the model of computation you're looking at. Okay, so that's how. So this was the first puzzle I wanted to discuss. And through this puzzle, what I basically showed you is one impossibility proof. Okay, and this is also called the counting technique, that you count a certain set of objects, in this case n placements of the watch. Then you say that, oh, there is a one-to-one mapping between this set and yet another set, which is the leaves of the tree. And then you say that, oh, if the two need to be matched, you need to spend at least so and so resources. Okay, so many such proofs exist in the literature. Okay, you may have seen similar proofs for, say, sorting requires n log n time under comparison models and so on. Okay. Great. So that was puzzle number 1.
Nutan, sorry to interrupt.
Yeah.
There were 2 questions about the puzzle.
Yes.
So somebody has pointed out that it should be probably floor of log n instead of log n.
Yeah, I am ignoring those things in the sense that I will ignore constant factors here and there. So n by 2 may be the same and so on. So up to that, but it's a very valid question.
And another question, which I think you have probably already explained, but still I'm asking. So how do we make sure that this method will surely work every time?
No, so it will not. Okay, this is not the only method to prove lower bounds. Depending on the model, you have to come up with a method. And as I showed you the very first question about graph coloring, we have no method to show a lower bound for that. Why n cube? We don't even have a method to show n square lower bound for that. So there are lots and lots of problems where actually we are lacking methods to prove lower bounds, in fact. And it's a great question in the sense, is there like a recipe to prove lower bounds? Though I may make it sound like that through this puzzle, it's really not the case. People, for this was a very simple example, of course. just to demonstrate why lower bound need to argue against all algorithms. So that was the point I was trying to make through this, but otherwise this lower bound was simple enough. But there are situations when the lower bounds are not very simple, and or there are models which are so intractable for our understanding that we are not able to show lower bounds, effective lower bounds even now. So this method may not always work, yes.
So there was another question, maybe you'll speak about this later. So was the problem about graph theory connected to P versus NP question? So this was another question.
Can you repeat the question?
So the graph colorability problem that you showed, was it connected? Is it connected to the P versus NP problem? Is the question.
Yes, in fact it is. I am going to talk about that later. It is very much connected to P versus NP question. Yes.
Okay. So I don't have any more questions now.
Okay, so maybe I will, what I'll do is I'll go to the next puzzle. Feel free to ask questions again. So we move to the second puzzle now. So here I'm going to give you one more example, maybe point out a few other subtleties about proving lower bounds. Let me tell you, both the puzzles indicate a lower bound technique, which is in itself quite easy. But it is just to demonstrate to you what goes on into a typical lower bound. Okay. So again, you have this annoying little brother, and because you lost so many chocolates to him the last time, you planned a very evil surprise for your brother on his birthday. So you say that, look, I have these n boxes of gifts, and either one of the boxes, either none of the boxes have any gifts, or at least half of them have gifts. Okay, and these gifts are going to be something really silly. So you say that, okay, if you tell me which one among the two it is, I will give you the real gift I have. Okay, you got a very nice gift for him otherwise, but he needs to tell you which among these two it is. And unlike the last time, where we could ask whether the watch is before this or after this, here the questions that he can ask you are limited. He can open a box at a time, and each box he opens, he has to give you one chocolate. Okay, so he cannot ask before this, after this, or anything like that. Everything is in front of him. He opens a box. If he opens a box, he has to pay you. All right, and of course, he may open a box, he may not find anything, etc. All of that is possible. Okay. So how am I doing with respect to time? Yeah. So great. So just to underline the model, okay, the kind of questions he can ask are, does the IIT box contain a gift? Alternately, he can just open the IIT box and see whether it has a gift or not. So here is a very simple strategy. He can just go on opening the boxes in some order. Let's say from 1, 2, 3, 4, etc. He can open first n by 2 boxes. If the answer is no, if all n by 2 boxes have no gifts in them, then obviously there are no gifts in all the boxes. Yeah, because you told that it can be only one of the two possibilities. The two possibilities were either none of the boxes have any gifts, or at least half of them have gifts. Okay, so after opening n by 2, if you see no gifts, naturally there are no gifts. Else, you will find one box with the pseudo gifts. Okay, and then he'll be able to tell which one of the two it is, and you will give him the real gift. So to get the final real gift, he has spent somewhere around n by 2 chocolates. Right? Now the question, the impossibility question, is posed where you are the receiving end. So you really don't care about this question, but your brother does. So can your brother pay less than n by 2 chocolates and figure out the answer? I should be slightly more precise here. Suppose he has already decided a strategy and written it down on a piece of paper. You know the strategy that he plans to deploy. Like in the previous example, we told what the strategy is going to be. Either we'll open one by one, or will deploy binary search, whatever it is. Similarly, he's also told you the strategy. He's told you the ordering in which he plans to open the gifts. He has decided a strategy to ask his questions. The question is now, can you place the gifts in a way that he must pay at least n/2 chocolates to you? Fair enough? Okay. So I'm coming to a slide where I'm going to show you this impossibility result. Yeah, why am I calling this an impossibility result? It's going to show to you that he cannot get away without paying n/2 chocolates to you. Fair enough? So you have this evil, devious plan, and I'm going to show how you can be very evil and devious in this. Okay. So what are we going to show? No matter what the strategy, no matter what strategy he deploys to open the boxes, there exists a placement of gifts such that you receive at least n/2 chocolates. So here again, we can actually depict the strategy of being deployed as a tree. Here, the boxes, the nodes of the tree ask, does the I1th box have a gift? Does I2th box have a gift? As soon as you get a yes answer, actually, he stops paying you any chocolates. Yeah, because that's the end. He sees one, then it has to be the option where there are n/2. Because the problem has only two sides. Either none of them have any gifts, or at least n/2 have. So if he finds even one gift, he knows he's in the second situation. So now, how shall I argue that it will require him to pay n/2 chocolates? Okay. So I'm going to tell you that in the next couple of slides. In this slide and the couple of overlays now. So the strategy is very simple in this case. Notice that for any ordering of opening the boxes, which is basically his strategy to play this game. Say the opening of boxes is I1, I2, IT, where T may be some number, maybe pretty small, 3, 4, whatever, or n/2 as you like it. You can set it the way you like. For any ordering of opening the boxes, say I1, I2, etc., notice that there is a placement of gifts in the rest of the boxes that will enforce a payment of T chocolates to you. This is often called the adversary argument. Adversary argument is for the decided strategy of the opponent, adversarially, you choose a position for the gifts to be put in a way that a certain amount of payment is mandated from your opponent. Okay, so this is called the adversarial strategy. And in fact, that shows you if you put T equal to n/2 in this. So this requires a one-line proof that for any ordering, there is a placement where T chocolates will be paid. But once you have that, by setting T equal to n/2, you have got a lower bound for this particular game. Okay. So this slide is coming to an end. This is the lower bound proof in this case. This was relatively simpler, but let me give you a little bit of flavor of the kind of problems that this problem relates to. Yeah, this seems such a simple problem. Okay, but it is a very interesting problem, and versions of this problem are even being researched on presently. Yeah, so it has beautiful connections to other things. So let me spend the rest of the some time of this puzzle just telling you a little bit about what this relates to. Okay. Let's look at this function, which I call promise OR function. Promise OR function takes n inputs. These are 0, 1 bits. And it outputs a 1 if summation xi is n/2 or more and 0 otherwise. This is precisely the function we were trying to compute. Yeah, this function is promise. It's called promise function because it's not defined anywhere else. You get only two types of inputs. So you're promised that the input will come from these two types of inputs. either summation xi will add to n by 2 or it will add to 0. Okay, so it's a promise input problem. And the task of the decider is to decide which among the two it is. Yeah. This, I mean, if I'm allowed to look at all the inputs, I have infinite memory and so on, then this problem is trivial to solve. But the kind of questions I'm allowed to ask are only look at a bit at a time. And every bit I query, I pay money for that. Okay. So what we did by asking queries was we created this tree, which is often called a decision tree. Okay. And we are asking what is the minimum depth decision tree that computes this function. Yeah. By that I mean, what do I mean when I say the tree computes the function? When the tree terminates, when all the leaves are labeled, it correctly computes for every input, that valid input it receives, it correctly goes to a leaf whose label is exactly what the function would have labeled it to be, that input to be. Yeah. So in the previous example, for instance, if it was all zeros, then your questions may have been 1, 2, 3, 4, and the tree would have gone down and no, and finally said 0. 0 to indicate that in fact the overall function is computing to 0 after n by 2 queries. Okay, so this is called decision tree. Decision tree is the structure I drew on the previous slide. And it is called deterministic decision tree because every question you ask is deterministically asked. It is asked based on the answer given to the previous one, but it is still a very deterministic process. Yeah, by asking the next, you already know what your next question is going to be, if the answer was that, and so on and so forth. And what we in fact showed on the previous slide was that to compute the promise OR function written on the top of this slide, at least n by 2 queries or n by 2 depth is necessary, or alternatively, deterministic decision tree complexity of this promise OR function is at least n by 2. Okay, maybe this is a lot of mouthful to digest right now, but the main intention of this slide is for you to go and Google search some of these terminologies and so on if you are interested. So that I just kind of threw around a few words here. So if you find some of these things interesting, then there is a lot going on is what I wanted to say through this. A little bit more, in fact, can be said. So decision tree complexity is a widely studied area, in fact. And if the same problem were to be solved but using randomization, that is, now your brother has some random numbers with him and he's allowed to use these random numbers to somehow query inside these boxes. So what he could do, for instance, is that he'll pick a random number between 1 to n. Okay, and then he'll ask you, if suppose that turns out to be I, then he'll ask you, open the box I. He'll pay 1 chocolate to you. Now, if indeed there were no chocolates present, no gifts present in any of the boxes, then with probability 1, it will be an empty box. On the other hand, if there were n by 2 gifts, there were boxes with n by 2, there were n by 2 boxes with gifts, then with probability half at least, you will pick a box that has a gift. So now your brother, by giving just 1 chocolate to you, with probability at least half, be able to figure out which one of the two it is, which one of the two cases it is. And in fact, if he was willing to give away 5 chocolates, he may conduct this random experiment 5 times and be sure with probability 1 minus, or he will go wrong with probability 1 by 2 to the 5. Yeah, every time the probability that he makes a mistake when there were more than half boxes with gifts, but he doesn't find any, is half times half times half times half times half. Right? So that is the probability of error after having spent 5 chocolates. So by spending k chocolates with probability 1 by 2 to the k, he would be wrong. But otherwise, by just spending 5 chocolates and using these random queries, he would get the correct answer with probability 1 minus 1 by 2 to the k. So this is called randomized decision tree complexity. And for promise or, randomized decision tree complexity is really small, as we kind of just hand waved our way through. How about this other function, which is the OR function? Why is this called the OR function? You may have seen the Boolean OR function of 2 bits, which becomes 1 even if there is 1, 1. It's just an n-bit generalization of that function, where you say that it turns 1 even if there is 1, 1 in the input. It is 0 only when all the inputs are 0. So in terms of the puzzle, either there is one box or one or more box with gifts, or none of the box have gifts. And now he's supposed to tell between the two. You will immediately see that the random strategy may not work anymore. Yeah, because what if there was only one box with a gift? The probability that you actually randomly pick that box is 1 by n. That's really small as compared to half in the previous case, because there were half of the boxes filled with gifts. So randomized strategy doesn't work. In fact, it is known that the randomized query complexity, randomized decision tree complexity of the OR function is n by 2. But now comes an interesting twist. People also considered quantum query complexity or quantum decision tree complexity of this. And I'm not going to define that. I'm not even going to give an example of that. But you may again go back and search for it. It is known that for the OR function that is on this slide, you have decision trees of depth only square root n, as opposed to n in the randomized case. And in fact, square root n is sort of tight and so on. Okay? And this has beautiful connections to other things in quantum computation, like Shor's algorithm, Chebyshev polynomials, and so on. So my whole point of just going through this was to tell you that there is a lot going on. Though I presented the simplest possible case of it in the slide as a puzzle, there is a lot that is going on. And if you find it interesting, you should definitely look into that. Okay. So now we come to the last section of my talk. So what we did in the beginning is we kind of saw why we should prove impossibility results. Yeah, cryptography and all of that. I did a little bit of a pitch for that. Then we saw through 2 puzzles, how to prove impossibility results. Yeah, and I kind of gave you other pointers to look at if you are interested. Now, let's look at the picture currently. What do we know about computational impossibilities? So turns out that what we know is merely a drop in the ocean. There's a lot to be proved. Okay, so there are classical results which show that there are problems that are computationally intractable. Okay, so there are problems for which no computer can solve it, however smart you may be. And in fact, very interesting thing about these results is that they were proved even before computers were invented in some sense, or almost simultaneously as the computers were getting invented. Right? And the proof technique is a proof technique known to mathematicians. So if you've seen why real numbers and integers don't have the same density, you would have seen this Cantor's diagonalization proof for that, which shows that reals are denser than integers. It's basically the same idea used in the language of computer science to show such a result. So it's quite a classical result. People notice that this Cantor's diagonalization can be used to make this computational statement. Right? Some others very interesting results are also known. They make the following type of statements. They say that for most reasonable resources that you can think of, say time or storage space or queries or energy or reasonable things that behave monotonically and so on. For most reasonable resources, there are problems solvable with more resources, which are provably not solvable with fewer resources. Okay? These are called hierarchy theorems. Okay, so suppose I give you there, so it is known, for instance, that there are problems that can be solved in time n to the 5, which are provably not solvable in time n square. Okay. Unfortunately, these are existential type results. So there is no specific problem that is known that is solvable in n to the 5, but it's solvable in n to the 5, but not in n square. But unfortunately, we only know existence of such functions or existence of such problems. Okay? This proof also goes through diagonalization. Okay, so what you say is that look at Cantor's diagonalization, add the computational language on top of it, which is really very cosmetic. So the previous slide thing is just a cosmetic rewording of Cantor's diagonalization, whereas this says that, okay, on top of that, think about a resource, time bounded or space bounded or whatever, and redo the diagonalization. Okay, so those type of results. Very interesting things happened in the world of complexity when complexity theory was not formally known as complexity theory around the time of Cold War. So Steve Cook in the US and Leonid Levin in then USSR discovered a large class of problems, okay? A set of problems such that all of them were intractable. Those were Cold War times, remember. So there were problems that were computationally hard, but military was trying to solve them, and rest of the people were at Bell Labs, and all that kind of backdrop. And so naturally, the two leaders or the agencies fighting each other, they were trying to solve these really intractable problems and so on. And they were not able to solve. Maybe it was believed that that time the computational power was less, but really they seemed very difficult. These people being mathematicians, theoreticians, there was no formal computer science department in most universities in the 70s and so on. It all started much later. So they were combinatorial set theorists and so on. They were in the math department, the electrical engineering department, professors in those places and so on. So Cook and Levin, again, they noticed that because they were kind of used to thinking abstractly, they also said that, okay, all these problems are hard to compute, but in fact, they are all related to each other. It's not like happening in a chaotic way. There is some sort of a reason or a rhyme behind why all of them turn out to be difficult. They are avatars of one another in some sense, in fact, is what they noticed. Yeah? And then they showed that they were incapable of showing that they are hard to solve. On the one hand, they are not able to solve them efficiently. They are all related to each other. So all these important problems either simultaneously will work out or simultaneously will not work out. And then on top of that, the bad news that they are all hard to solve. Yeah, they called all these problems NP hard problems. Okay, and these problems we even today don't know how to solve efficiently. And this is the thing that I mentioned earlier, like this problem we saw earlier. This is called a graph coloring problem. And so some versions of this are slightly known and so on, but widely this problem is open. We don't know how to answer both the questions listed on the slides and many, many other things about this problem, unfortunately. And this is also an NP hard problem. And so impossibility results made their appearance in the form of this theory that of NP hardness. Can we show that there is no efficient algorithm for NP hard problems? Okay, so this question got posed, a whole area sort of originated from inquiries of this nature and so on. Okay, so as you may have seen some of these posters somewhere where you climb this hill and then you get somewhere and then you see, oh, the actual peak is still up ahead. Something similar is the story in the case of lower bounds or impossibility results in computer science. So in the 40s and 50s, this Cantor-like diagonalization proof revealed that there are intractable problems. As I said, this was simultaneously happening while computers were being built. This is World War time and so on. In the 70s, this whole theory of NP hardness and came up. Even the hierarchy theorems that I told you, that more resources are strictly more powerful than fewer resources for reasonable resources, that hierarchy theorem I told you about, these were also discovered around 70s. In the 80s, one profoundly new technique was developed, and a very famous result of many others, so I have not written a name there, but first unconditional lower bound, as they call it, was shown. And then it took several years, many others. So this picture is in some sense not the right one, but for every peak there are many sub peaks and many other flags that should be put there. But of course, in a talk like this, I don't want to go into the details. But then there was a massive breakthrough in 2000s, in fact 2010, a decade ago now, which showed another very nice unconditional lower bound result. Turns out where we would like to be is sort of quite far still. So where sort of we can provably show cryptography is safe, or we can provably eliminate randomness from computation. And these are questions people want to look at. These are still far, I mean, they're really far as one feels right now, at least. Okay. So now this is my last slide. So now I would like to say that this talk, you should think of this talk as an invitation to come and prove impossibility results in computer science. Okay, what is the road ahead? So what could you bring to the table? Yeah, there is many years of research, but still there is so much not known. So obviously everybody, a new eye, will definitely bring something new, more richness to the area for sure. So as I said, we have these few techniques we know how to play around well with, but a foundationally new technique would be wonderful. There have been such breakthroughs, as I showed you with those 4 peaks, but something new is of course required. Another very interesting place where we could contribute as computer scientists would be finding connections between computational impossibility and other areas. So, for example, in the last 2-3 decades, such extremely beautiful results have come out, which I could not show naturally in that picture, of the nature that, okay, if I'm able to show impossibility results, then something else happens. Okay? Like connections to cryptography, there are connections to pseudo-randomness, there are connections to many other beautiful areas. That's one way to contribute. Another way would be that, oh, if you are able to do these other things, then you will be able to prove lower bounds. Such results are also known. And contributing, so techniques that imply lower bounds and things that get implied by the lower bounds. So all these sort of connections will make this picture much more rich than it is. And really, there is room for everyone. And especially if you are a mathematics undergrad, I'm sure this area is something you, and if you like this area, it will certainly find room for you, because there is so much to be figured out. So with that, let me end my talk. Thank you very much for listening.
Thank you so much, Nutan, for the very nice talk.
Thank you.
And the very interesting puzzles that you showed us. I have several questions, so I have collected a few of them. And I mean, going back to the second puzzle, so the question is there a non-deterministic version of this question, and are the two complexities different for the deterministic and non-deterministic version? And with that also, if you could say what a non-deterministic version looks like.
Okay, so in general, non-deterministic version is there is a like a all-knowing, or there is a person who is willing to supply you with the proof of a certain fact. So for example, okay, let me take a slightly different model where there are 2 people, Akbar, Birbal, and they each have one string with them, and they want to check whether their two strings are unequal. Okay, so in this case, a non-deterministic, this is called the communication model, where they are supposed to send bits to each other and then at the end figure out whether their answer is something or the other or not. In this model, if there is a non-deterministic, if this is to be thought of in the non-deterministic sense, then what happens is this non-deterministic, there is a prover. Okay, this prover can communicate with both of them. He is all-knowing, so he knows everything about their inputs and so on. In a non-deterministic world, this non-equality of two strings can be easily checked by the prover sending an index of a position in their inputs, say I. And now both of them just need to send that bit to each other. When they send the bit to each other, either it is the same or not. And if this is a correct non-deterministic protocol, then what happens is the prover has no incentive to lie when it is a valid non-equality input. So he will just send the index where they differ. And by just using one extra bit of communication between them, they will figure out whether their inputs are distinct or not. So non-determinism in general is this setup where you have a prover and then there is a resource-bounded verifier. Prover is not resource-bounded. And in the case where the input is a valid input, the prover doesn't have any incentive to lie. On the other hand, when it's not a valid proof, the prover still wants to convince you that it is a valid input. So think of the prover as a student and the verifier as a TA. And suppose they are supposed to suppose there is an exam question, so the student will always try to prove it. So if there is a prove that question in the exam, the student will try to put some proof. And now, of course, if he is able to prove it correctly, the student has no reason to lie. So student is like the prover here. But if he doesn't know the answer, he will still try to put in a proof which convinces you. And then as a verifier, as a TA, it is your job to check whether it is the correct answer or not. So typically, the non-determinism is depicted in this format. So in the decision tree world also, there is a non-deterministic version, and the complexity is lower. But it depends on the function also.
Thank you. So another question which was asked during the second puzzle was that do all problems in computer science have such tree structures?
No. So that's not true. There are many cases. So, but usually there will be some sort of, if there is a nice combinatorial object sitting underneath, it is easier to argue lower bounds for. So though we are not lucky enough to have that structure every time, when there is such a structure, it's easier. But yeah, it's far from true that there is such a structure, always.
The next question is there any connection between Russell's paradox and Cantor's diagonalization argument?
So Russell's paradox, if I'm not mistaken, is so what is Russell's paradox? Sorry.
So I'm not sure what. So this was asked by Vishal. So is it the Barber paradox, Vishal, or the set paradox?
Yeah, I guess both.
Okay. So
okay.
Yeah.
I don't know exactly how to answer because I'm not sure which one you're talking about. But Russell's paradox, and which one did you say?
So self. What I mean is maybe
I see.
a bit about self-reference.
Okay, no. So okay, I think the paradox I have seen is in set theory. Is that the right one? Then? Russell's paradox in set theory, is
Yes,
that one?
yes, and there's also a version which is like there's a barber in a city who says that I only shave those who don't shave themselves.
Right. Okay. Yes. I now I know what you're talking about. But so I don't think there is a direct thing. But okay, what I can definitely say is, one has to self-negate one's answers along the diagonal. Like in the when we say that reals are denser than integers, what we do is we sort of say that, oh, maybe they are not. So let's enumerate the reals, say within 0, 1 interval, and now I'll take this diagonal and I'll invert the diagonal. And this will give rise to a new real number which is not enumerated over here. And that will show that reals are denser than, so this is the typical diagonalization. So I don't see any connection immediately between that and Russell's except for self-negating a certain predicate, I guess.
Thank you.
If somebody in the audience sees, then they can mention that, I guess.
This question was asked a few times. I mean, how is it connected to cryptography? How is everything that you say connected to cryptography?
Okay. So cryptography often I'm not a cryptographer, so let me clarify that. But from the general popular thing. So what happens in cryptography is that you are given the existence of a hard function. For example, you are told factorization is difficult, and then you may have seen things like RSA cryptography or some public key cryptography, where what happens is you take a function f which is easy to compute, but f inverse is hard. Okay? Now what one does is they apply f in one direction, but then put the onus of having to compute the inverse on the adversary, thereby making it difficult to crack in a very vague sense. So in general, for example, RSA cryptography, which now is broken by very efficient computers and so on. But the main crux of the thing was it was computing a large number, which was multiplying many numbers. And now because factorization is difficult, inverting this multiplication is difficult, the security of the protocol could be proved under the assumption that factorization is hard. Now, because larger and larger numbers are computers are able to factor, RSA has become sort of very vulnerable and now harder and harder problems. So, but in any case, having the existence of hard functions, which are called one-way functions. Yeah, one-way functions are the best case situation for one slice of cryptography. And if you have one-way functions, then certain kind of cryptographic protocols are secure. So the connection is having hard functions ensures security of the encrypted messages. That it becomes difficult to crack the messages for an adversary, even if the entire encryption is visible. The decryption is the hard part. The inversion becomes hard. So, and most of the cryptography we do today is under the assumption that such hard functions exist. So if, say, tomorrow certain hard functions are shown to be easy to compute, which is instead of impossibility results, upper bound results come about, then those the cryptography predicates that depend on some of these assumptions will be rendered useless or rendered weak for cryptography.
Let me take this opportunity to advertise a upcoming talk on 10th of October, so which will be given by Dr. Shweta Agarwal of IIT Madras, and she's going to speak about cryptography.
Great.
So I have a few more questions.
Sure.
So one question was, what is Shor's algorithm? If you could say in very short, how
okay. I don't know how to say it very short, but it's like a search algorithm. Yeah, I don't know how to say it very short, I guess.
But I have given the link to the Wikipedia page, I think, in the chat.
Yeah, I think that will be a good resource for just a upper level view. I think that is, yeah.
So there is a question that about this last but one slide that you showed, and where you spoke that about the major breakthrough result in the 2010 that was
Yeah.
So what was that result exactly?
Okay, so that result was proved by Ryan Williams, and what he managed to show was, I mean, we want to separate, say, NP hard. We want to show NP is not in P. Suppose, yeah, that is like saying the three colorability cannot be solved in polytime. So we want to separate these two classes. But instead of NP, suppose I go to the next really large non-deterministic class called NX. Yeah, so it's like we want to say that the elephant is stronger than a mouse, but instead we go to a dinosaur and an amoeba, and we say that dinosaur is more powerful than amoeba. Okay, so I mean, this is a major breakthrough result. So not to say that it is proving anything weak. It's just that we don't know how to separate two very close classes such as P and NP. But what this result very beautifully achieved was it separated a slightly larger class called NX from a slightly lower class than P called ACC. And it showed that these two classes are provably distinct. So we want to show P is not equal to NP, but it was able to show some other higher class is provably distinct from a slightly lower class. So that was the result. I can supply you the link of the abstract. The author has given beautiful talks on this. He's a wonderful speaker. So you can also look at those if you are interested, if the audience is interested.
So could you please tell me the name once again? I can write it in.
Yeah, Ryan, Ryan.
Yeah.
Williams.
Okay. So I have one final question. So this is from my side, actually. So for a beginner, what sort of books or resources would you recommend to get into this area?
That's a great question. So as a prerequisite, I think it's good to know a little bit of combinatoric discrete math, these kind of topics. If you actually want to learn complexity theory and you want to go directly towards lower bounds, there are 2-3 very nice books. So there's one book by Stasis Yukna. This is for circuit lower bounds. I can share the title of the book with you later. So this is a good book to kind of start with and look at some lower bounds. If you want to do classical complexity theory, know more about P, NP, and resource bounded computational classes and so on, then there is a very nicely written book of Sanjeev Arora and Boaz Barak. This is called, I think, Introduction to Complexity Theory, a Modern Approach. So that is often used to cover the basics of complexity theory in most complexity theory courses also. So that's a nice book to read as well. There are very nice courses that have been offered by people around the world, and there is specifically one course which is called Tcs Toolkit. So it is a course offered by this person from CMU, Ryan O'Donnell. It's a beautiful course, around 25 lectures, I think, overall. And it gives a detailed description of basic toolkits used by complexity theorists or thereabouts people for making headway into this area. So that is a very nice course. I mean, even if you don't get into the area, you will learn very interesting things there. So that may be another resource to check out.
So I have shared the link of Arora and Barak's book, so it's available in their website. So if
there is a draft that is easily available for free download also, and also of the other book which I can send you later.
So I have got one more question while you were saying about this. So somebody is asking, this is not related to what you say, but somebody is asking if you could please tell a little bit about the unique game conjecture.
Okay. Unique game conjecture. So again, I don't know how to give a short answer for that, but okay. So just a thing to plug in the sense of in whatever I've talked about in terms of that is that so you want to show that certain problems are not they are, suppose we give up on problems that are NP hard, then we are going nowhere. So what we could instead say is that, okay, can you give an approximate answer to those questions? So for instance, suppose you want to say that whether what is a good question? So is there a graph, given a graph, is there a set of vertices of size k, say, such that all the vertices in that are connected to each other? This is called a clique problem. And this is also known to be NP hard. Now, I don't know how to solve this, but then I'm okay with an approximate answer. So, you tell me whether there is a clique of size approximately k, say. Or there are different versions to it, the ways to define this. I'm not saying it all right. But So in the case of approximation theory, where you want to say whether there are whether one problem can be approximated well or not, that's where unique game conjecture features, and it talks about it gives connections to whether in the approximate sense problems are hard or not. So let me leave it at that. Again, a Wikipedia page does very good justice to unique games conjecture, and I will require a little more time to maybe say that well, unfortunately. Yeah.
So I don't have any more questions at the moment. Let me formally thank you again for the very nice talk and for answering so many questions and also giving your valuable time.
No, thank you for inviting me. I think I had a great time myself. Yeah.
So I'm now